Hi Bobcats, this video is going to introduce the idea of valence bond theory. Our objectives are to describe bonding in terms of orbital overlap and to look at the symmetry of the orbital overlap to classify the bond as either a sigma bond or a pi bond. Valence bond theory focuses on the idea that bonds can be formed when an orbital from one atom overlaps with an orbital on another atom, and a pair of electrons can simultaneously occupy both orbitals. Graphs like this one are often shown to illustrate this idea and to illustrate what we mean by a bond length. If you have two hydrogen atoms that are separated by a large distance, so we're talking about things that are over here on the right-hand side of this diagram, the part labeled A, the energy of interaction between them is essentially zero. If the hydrogen atoms are far enough apart from one another, one atom is completely unaware of the existence of the other atom. And so this horizontal axis is plotting how far away those atoms are. So if we start moving to the left along this horizontal axis, it means that we are getting the atoms closer to one another. So if we look at situation B, the atoms are getting close to one another, but their orbitals are not, that 1s orbital from each is not beginning yet to overlap with the other. But as they start getting close, the electrons in one atom start to feel the nucleus of the adjacent atom, and so there starts to be a little bit of attraction going on there. And so this red line down at the bottom is showing the energy of the system. And so as the electrons in one atom start to experience an attraction for the nucleus of the other atom, that energy starts to drop a little bit. As the atoms continue getting closer, we will reach a minimum in this energy level diagram when we're at the distance that corresponds to this minimum in energy. Well, that's what we call our hydrogen-hydrogen bond length. It is showing how far apart those two atoms are at this minimum, and the atoms are close enough that their electron clouds or their orbitals are overlapping just a little bit. However, if we continue to push these atoms closer to one another, as we're showing here in part D, now the nuclei start to experience repulsions for each other, which causes the energy of the system to go up. And so this curve really does have a minimum where we're balancing the attractions of the electrons for the other nuclei with the repulsions of one nucleus for the other nucleus. And so at this energy minimum, the two atoms are close enough that their orbitals are overlapping a little bit, and this is where we say that a bond has formed. There are a couple of different ways that orbitals can overlap, and I'd like to kind of illustrate it with a series of diagrams. The first one of these is known as sigma bonding. We're going to use the lowercase Greek letter sigma for that. The way that we identify sigma bonding is that the electron distribution is cylindrically symmetric. And I'll explain a little bit more what that means in just a moment. So in this first row, what I'm trying to show is two hydrogen atoms with their 1s orbital. If these two hydrogen atoms move a little bit closer to one another so that their orbitals start to overlap, we end up with something like this, what's drawn here on the right, which we will call cylindrically symmetric. If we were, think about it this way, if we were to put these two atoms that are in this bond on a skewer, and that skewer went through both nuclei, and then we were to rotate the bond around that skewer, we just started spinning the skewer, it would look the same no matter what angle we rotated it through. And that's how we identify something as being cylindrically symmetric. If we can rotate it along that internuclear axis, and we see the same electron distribution. It's cylindrically symmetric, and we're going to call that a sigma bond. So one way that sigma bonds can be formed is by the just the overlap of s orbitals from one atom and the next. Another way, now I guess I should probably label these orbitals too. It's an s orbital and an s orbital. Another way, oh yeah, and then this would be our sigma orbital. Another way that they can overlap is an s orbital can overlap with one end of a p orbital. And so if these move close enough to each other that we're seeing overlap between them, this resulting orbital will be a sigma bond, because if we skewered all of the nuclei and rotated it along that skewer, we would be seeing the same thing no matter what angle we rotated it at. And then the other possibility is that we could have a p orbital on one atom overlap with the p orbital on another atom, and they're going to overlap head to head. That also would be cylindrically symmetric. And if you look at the rotation about there, it's the same no matter what angle we're at. So these are three different ways that we could end up with a sigma bond. We could overlap an S with an S. We could overlap an S with the P going with the head of the P, or we could overlap two P orbitals head to head. So let me just go ahead and make a note of this, that this has to be head to head on the P's for it to be cylindrically symmetric. The other type of overlap that we can have with p orbitals, if we have two p orbitals on adjacent atoms that are lining up side by side, if they get close enough, their electron clouds can start to overlap side to side, which is what those teal areas are trying to indicate. One of the really cool kind of things about these pi orbitals, or this pi bonding, is that we actually end up with what's called a node right along that internuclear axis. It means that there's zero probability of finding the electrons along that internuclear axis. That's okay, that's where the sigma bonding is taking place. The pi bond doesn't need to be there. And we end up with two big lobes of orbital density, or of electron density. Just like a p orbital has two lobes with it, well, the pi bond has two lobes to that electron density. And yeah, a key phrase here, side to side overlap for our pi bond. With valence bond theory, we're going to describe bonding in terms of orbital overlap. If the overlap of orbitals is cylindrically symmetric, like s orbital overlapping with an s orbital, or the head-to-head overlap of p orbitals, we're going to call that sigma bond. If it's not cylindrically symmetric and we end up with this kind of scenario where there's a p orbital on one atom, p orbital on the next, and the p orbitals overlap side to side, we're going to call that type of overlap a pi bond.